Ordered rings and fields. We say that a ring, R together with addition and multiplication, is ordered if there is a non-empty subset P of R satisfying the following three properties. 1. If A and B are in P, then A plus B is in P. 2. If A and B are in P, then A times B is in P. And 3, if A is in R, then exactly one of the following holds. Either A is in P, A is 0, or negative A is in P. R plus we define to be P, the positive elements of R, and R minus we define to be the set of A and R such that negative A is in P. These are the negative elements of R. As an example, let R equal Z, the set of integers, and let P sub Z equal the set consisting of the integers starting at 1, 1, 2, 3, and so on. Then it's easy to see that the three properties are satisfied, right? If you add two of these numbers, you get another one. If you multiply two of these numbers, you get another one. And if you take any integer, either it's in this set P sub Z, or it's equal to 0, or its negative is in this set P sub Z. It follows that the set of integers together with addition and multiplication is an ordered ring. Theorem: the set of rational numbers together with addition and multiplication is an ordered field. We already know that this is a field and that it's an ordered field. Although it's not too difficult to prove, it does involve a lot of technicalities that I don't want to get sidetracked with in this video, so I'm going to leave the proof of this out for now. If R together with addition and multiplication is an ordered ring, and P is the set of positive elements from the ring, we will write A greater than 0 instead of A and P, and A less than 0 instead of negative A and P. That's probably a notation you're more familiar with. If A minus B is greater than 0, we'll write A greater than B or B less than A. And we write A greater than or equal to 0 if A is in P or A equals 0. We write A less than or equal to 0 if negative A is in P or A equals 0. And we write A greater than or equal to B or B less than or equal to A if A minus B is greater than or equal to 0. So using this new notation, the first property can be written: if A and B are greater than 0, then A plus B is greater than 0. The second property: if A and B are greater than 0, then A times B is greater than 0. And the third property: if A is in R, then exactly one of the following holds. Either A is greater than 0, A is equal to 0, or A is less than 0. We may use the notation R less than or equal to for an ordered ring. Note that plus and times aren't explicitly mentioned, but of course they are still part of the ring. Also, we may just use the name of the set for the whole structure when there is no danger of confusion. For example, we may refer to the ring R or the ordered field F instead of the ring R plus times or the ordered field F less than or equal to. Theorem 5.2. Let F less than or equal to be an ordered field, then for all x in F star, x times x is greater than 0. Remember, F star consists of the non-zero elements from the field. Okay, let's prove this. There are two cases to consider. First, if x is greater than 0, then x times x is greater than 0, simply by property 2 of an ordered field. That was the easier case. Second case, if x is less than 0, then negative x has to be greater than 0 because it's an ordered field. And so negative x times negative x is greater than 0, again using property 2 of an ordered field. We have negative x times negative x is equal to negative 1x times negative 1x. Now, it's not completely obvious that negative x is equal to negative 1x. You should definitely check this. Now, this is equal to negative 1 times negative 1 times x. This does follow from the fact that we have associativity and commutativity of multiplication. Now, this is equal to 1 times x. And here you should definitely check that negative 1 times negative 1 is equal to 1. We haven't proved this yet. And 1 times x is just equal to x times x. And here we are using the multiplicative identity property. So again, we have x times x is greater than 0, right? Because we already showed negative x times negative x is greater than 0. And then we showed that negative x times negative x is equal to x times x. So we must have x times x greater than 0. Theorem 5.3. Every ordered field, f less than or equal to, contains a copy of the natural numbers. Now, intuitively, that should make sense. You sort of have the natural numbers sitting inside of every ordered field, or some copy of it. But let's just make that a little more precise mathematically. Specifically, f contains a subset n bar consisting of the elements little m bar, such that n is in the set of natural numbers, such that for all n and m in n, we have n plus m bar equal to n bar plus m bar. N times m bar is equal to n bar times m bar. And n is less than m if and only if n bar is less than m bar. Let's go ahead and prove this. Let f less than or equal to be an ordered field. That's our opening statement. By the definition of a field, 0 and 1 are in f, and 0 is not equal to 1. That's one of the field properties. We're going to let 0 bar equal 0 and n bar equal a sum of 1 n times. And we'll let n bar equal the set of little n bar such that n is in n. Then we have that n bar is a subset of f because we know that 0 and 1 are in f, and f is closed under addition. So whenever we add up 1 a bunch of times, we know that we stay inside of the field f. Let's first prove the first part here by induction on m. So we first prove by induction on m that for all n and m in n, n plus m bar is equal to n bar plus m bar. Base case, k equals 0. N plus 0 bar is just equal to n bar, because whenever you add 0 to any natural number n, you just get n. And that's equal to n bar plus 0, because 0 is the additive identity for the field f. And by definition, 0 is the same thing as 0 bar, so we can write that as n bar plus 0 bar. Now the inductive step. Suppose that n plus k bar is equal to n bar plus k bar. So we want to show the same statement with k replaced by k plus 1. So we have n plus k plus 1 bar, and here we use associativity of addition in the natural numbers to rewrite that as n plus k plus 1 bar. And by definition of bar, we could write that as n plus k bar plus 1. And that's equal to m bar plus k bar plus 1. Here is where we're using the inductive hypothesis. And using associativity inside the field F, we have that this is equal to m bar plus k bar plus 1, which, again, by the definition of bar, is n bar plus k plus 1 bar. So we did it. By the principle of mathematical induction, for all natural numbers m, n plus m bar is equal to n bar plus m bar. Let's do the second one. Similarly, we prove by induction on m that for all n m in n times m bar is equal to n bar times m bar. Base case, k equals 0. N times 0 bar is just 0 bar, because any natural number times 0 is 0. And that's equal to m bar times 0 bar, because in a field, whenever you multiply a field element by 0, you get 0. That's something you might want to prove. Inductive step. Suppose that n times k bar is equal to m bar times k bar. Then we have n times k plus 1 bar is equal to n times k plus n bar. Here we're using distributivity in the natural numbers. That's equal to nk bar plus n bar. Here we're using the fact that we already proved the previous statement about addition. And that's n bar times k bar plus n bar. That's where we're using the inductive hypothesis. Now, using distributivity in the field, we get that this is equal to n bar times k bar plus 1, which is m bar times k bar plus 1 bar by the definition of bar. And by the definition of bar again, that's equal to m bar times k plus 1 bar. So we've done it by the principle of mathematical induction. For all natural numbers m, n times m bar is equal to n bar times m bar. Okay, now we want to show the last one. We want to prove that for all n and m in the set of natural numbers, n is less than m if and only if n bar is less than m bar. This is going to require a couple of steps. We first note that for all n and n plus 1 bar is greater than n bar, because n plus 1 bar minus n bar, by the definition of bar, is equal to m bar plus 1 minus m bar, which is 1. And that's equal to 1 times 1, because 1 is the multiplicative identity for the field, which is greater than 0 by the theorem we just proved, theorem 5.2. Right? Remember that theorem 5.2 says that for all non-zero elements in an ordered field, the product of that element with itself is greater than 0. And in particular, since 1 is an element of the field that's not 0, 1 times 1 is greater than 0. We now prove by induction on n that for all n and n with n greater than 0, we have n bar greater than 0. Base case, k equals 1. 1 bar is equal to 1, which is equal to 1 times 1. We just did this, which is greater than 0 by theorem 5.2. Inductive step. Assume that k bar is greater than 0. Then k plus 1 bar is equal to k bar plus 1 bar is equal to k bar plus 1, which is greater than 0. Here we used order property 1 together with the fact that we know that k bar is greater than 0 by assumption, and 1 is greater than 0, which we have shown a couple of times already. By the principle of mathematical induction, for all natural numbers n with n greater than 0, we have n bar greater than 0. Conversely, if n bar is greater than 0, then n is not equal to 0. That's because 0 bar is equal to 0 by definition. Since n bar is defined only for n greater than or equal to 0, we have n greater than 0. So we have shown that for n in the set of natural numbers, n is greater than 0 if and only if n bar is greater than 0. Next, note that if n is less than m, then m bar is equal to m minus n plus n bar. I used the standard advanced calculus trick here. I sort of just rewrote the expression by putting in what I wanted to be there and then undoing the damage. And we'll see why I did that in just a moment. This is equal to m minus n bar plus n bar, right? Because that was the first thing that we proved that we could do that. It follows that m minus n bar is equal to m bar minus n bar. I got that last equation by subtracting n bar from each side of that first equation. Finally, we have n less than m if and only if m minus n is greater than 0, if and only if m minus n bar is greater than 0, if and only if m bar minus n bar is greater than 0, if and only if m bar is greater than n bar, if and only if n bar is less than m bar. And we're done. One more theorem, theorem 5.4. Let f less than or equal to be an ordered field, and let x be an element of f with x greater than 0. Then 1 over x, or the inverse of x, multiplicative inverse of x, is greater than 0. All right, let's write the proof of this. Since x is non-zero, 1 over x, which is x inverse, exists and is non-zero. Assume toward contradiction that 1 over x is less than 0. Then negative 1 over x is greater than 0. Then x times negative 1 over x is x times negative 1 times x inverse. Okay, you might want to show that negative 1 over x is equal to negative 1 times x inverse, which is equal to negative 1 times x inverse. Here we're using commutativity and associativity of multiplication in the field. That's equal to negative 1 times 1. Here we've used the inverse property, which is equal to negative 1 using the fact that 1 is the multiplicative identity. Since x is greater than 0 and negative 1 over x is greater than 0, we have negative 1 equals x times negative 1 over x greater than 0. So 1 is not greater than 0. But once again, by theorem 5.2, 1, which can be written as 1 times 1, is greater than 0. This is a contradiction. Therefore, 1 over x is greater than 0.